It's Yan Dongguo again. Today, I'll continue talking about the Bayesian estimation as the very last lecture for this semester. Again, here's my email address. If you have any questions, feel free to email me at guoy@purdue.edu. Let's go back to the document camera. Today I'll continue talking about the Bayesian segmentation. The last subsection is called maximized likelihood parameter estimation with Stochastic EM. First of all, I would like to go back to the objective of this entire chapter again. So we have a random field denoted by vector x. This is our unknown, or the random variable we need to estimate. For each of the random variable, which is denoted by xx, so x is a lattice index, means this is x element in this vector x. And for each of them, we have one observation y. For each of x's, we have one observation yx. And given yx, we want to estimate x. So the basic probability model we use is here. We know given x what does y looks like, which is called likelihood term. And we have basic assumptions on the nodes here. Yes, this is the prior term. Combine the likelihood term and the prior term, we can get the probability model. That's the top. This is the model, so-called model-based image processing. And one advantage of this model-based method is that the model parameters can be estimated during the inverse procedure, which means we can estimate the parameters in this distribution and this prior distribution during the reconstruction procedure. Therefore, I introduce two parameters. One is the speed, the other one is theta. So the speed is a parameter in the likelihood term, and this theta here is a parameter of the prior distribution. So for this particular model-based probability, we have two parameters to be estimated. One is speed, the other one is theta. If we already know speed and theta, how to estimate x? This strategy was covered by the last lecture I gave. There are two possible methods. One is map estimation. The other one is NPM. So I will review the NPM very quickly because NPM has a strong correlation with the stuff we're going to cover today. So if the speed and theta are known, how to estimate x? How to estimate x? Here's the top function we propose. X, this x here is a ground truth. And this x hat is our estimator. We compare each element in the ground truth and each element in the estimator, and whenever they are different, this delta has value 1. If xs does not equal to xs hat. So if delta equals to 0, if they are the same. By minimizing the expectation of this cost function, we can get an MPM estimator, which is called maximizer of posterior marginal. Then I'll show you how to get this estimator from this cost function very quick. Last time I showed how to get the map estimation from the cost function from another cost function. But from this cost function, I'll show you very quickly. So what we are trying to minimize is the expectation of this cost function. We want to minimize this. And according to the fundamental definition of expectation, this can be standardized This is just because the linearity of the expectation. From this term to this term is a definition of the expectation. Step 1 is because of the linearity of the expectation, and step 2 is according to the definition. And again, how do we define the delta function? Whenever x does not equal to x hat, the value is 1. Right? So we want to minimize this term. This term equals to and minimize this term, and because whenever they are not equal, the value of this term is 1. Therefore, this term equals to this term here. So when x does not equal to x hat, this is the probability of the margin, of posterior margin. And by minimizing this term, it's equivalent to maximize this marginal here. This is how we get the MPM estimator from this cost function. And how to get this marginal? It's very computationally expensive because the only thing we know is the joint distribution of x and y. But in order to get this marginal, or in order to get the closed form of this marginal distribution, we need to calculate a lot of integrals to get a marginal. It's too expensive. So our solution is to approximate this marginal by this normalized histogram. Now how do we get this term? This x-x is a superscript L, means that we draw samples according to the given distribution of x. We draw samples a lot of times. We draw samples L times. And we estimate a histogram of this x-axis. Then we use the histogram to approximate this marginal posterior. So the x-axis, the final answer of MPM is x-axis is assigned with R max x-axis. It's obtained by this equation. This is ensured by the large number law. actually a strong large number law. And this is almost surely converged, as I proved in the last lecture. So whenever the distribution is very complicated or hard to get a closed form, this sampling strategy is very widely used. Not only for this particular problem, but even I assume during your research in the future, it's possible that you will meet another complicated distribution. Again, this sampling method is a very widely used solution to approximate this complicated distribution. If we have time, by the end of the lecture, I'll give you other optional methods to approximate posterior distribution. And so MDM needs us to know the parameter value phi and parameter value theta. But actually we don't. We don't know the value. We want to estimate from the model or from the data. Learn the parameter from the data. So if X is given, let's go back to the probability model here. If this X is given, Y is observation, Y is already known. How to estimate the phi and theta? It's very simple. Everything in this equation is known except phi and theta. We just use the maximum likelihood estimation to estimate it. Right? We already know Y and we already know X. We can estimate it. But unfortunately, for this particular problem, we don't know X. X is the thing we are trying to estimate. The only thing we know is Y. So this becomes a very typical incomplete data problem. And for this incomplete data problem, a typical answer or typical solution is the expectation-maximization method, which is called EM. So this lecture also serves like the review of all the stuff we have learned in this class, since this is the final one. So I'll review the EM algorithm again. So what is the basic procedure of EM? We have two steps. One step is E step, one step is M step. Why do you call the first step E step? It's short for, yeah, exactly, it's short for expectation. The answer is right here. The expectation of a what? Exactly. The expectation of a log of the posterior or a log of likelihood. And now, okay, if you see this equation, okay, you'll see, oh, this equation is crazy. Too many things in this equation. I don't quite understand what's going on here. I got confused. I'll explain this equation one letter by one letter. So we don't need to like remember the entire chapter of chapter 8. The only thing, the most critical part is to understand this particular single one equation. Okay, is Y known here? Yes. Yes, Y is known, so it's trivial. Is X known? No, this whole point, X is unknown. X is random variable. It's unknown. And how about this theta? This theta is a parameter we try to estimate. So this is expectation of what of a random variable. Start with letter F, letter U. Yeah, exactly. So it's expectation of a function of random variable. Here is the function of the random variable X. We want to calculate the expectation of this. So we just put the distribution or the probability distribution of x here and calculate the integral. It's very simple. And fortunately, it's an iterative method. We already have an initial guess of this parameter theta. So the distribution of x is given. And the function of x is given. Therefore, we just calculate the expectation of the function of x. And after calculating this expectation, what kind of stuff we get? We get another function of theta. After calculating the integral of over x, we get rid of x. X is unknown, but we get rid of it. We know the distribution of x, and after calculating the integral, x is disappeared. So after calculating this expectation, we obtain a function of theta, which is defined as Q in our class. And this Q is also called substitution function, which is always the upper bound of the original one. There is a more rigid proof in the textbook. So since it's a review, I don't think I have time to go through the proof in detail. So each step we get a function of theta, of the parameter. And m step, what does this m stand for?
Maximization.
Yeah, exactly. M stands for maximum. How to estimate theta parameter from this function Q? We just find the theta which can maximize this function. That's it. Then we get another theta, or feed this theta back to the E step again. We do this iteratively until converge, and it can be ensured to be converged. So this is the basic procedure of EM. And I'll give you an example to show how this works. And again, this example belongs to chapter 8. If you can understand the stuff in chapter 8 very clearly, understand the stuff I delivered in the last lecture, which is NPM, very clearly, the stuff in this lecture is very clear. Okay, how to estimate the parameters in Gaussian mixtures using EM algorithm. Okay, here we have a likelihood term. Y is observation, S is unknown, and it belongs to the nth data point, nth sample. And we have a parameter theta here. How to estimate it? Okay, first step, we calculate the Q, which is function of theta, by calculating the expectation shown in this equation. Okay, we have initial guess of theta prime here, therefore we have a distribution of x. Then we substitute this log likelihood by its original form here, and calculate the expectation. Eventually, this is the term we get. And see, in this term, we don't see x. And after we get this step, we can estimate all the statistics or all the parameters of the Gaussian mixture. Just two steps. Okay, here comes the following question. How many parameters or how many parameter sets we have for the model we propose here? We have two parameter sets, not only theta but also phi, right? And if you keep looking at this probability model, we can see that this probability model is decomposed into the summation of two terms, likelihood term and prior term. Therefore, we do not need to estimate the likelihood or the expectation of the likelihood of the entire term. We can do them separately, which can make our algorithm even faster. I'll show you two steps implicitly here. Okay, the first step is we are trying to estimate phi. The second term here has nothing to do with the parameter phi. The only important term is the first term here. Therefore, first of all, we calculate the likelihood, the so-called loss likelihood, using the given phi k and theta k. We calculate expectation, and we obtain a function Q1, which is a function of phi, and given value phi k and theta k. And in order to estimate the parameter theta, here, we don't need the first term, because the first term has nothing to do with the theta. We only calculate the expectation of the log of the distribution here. We get a Q2, which is a function of parameter theta, given phi k and theta k. After we got these two functions, the two Q functions, we can update the estimation or estimator of the parameter phi and theta using the maximum likelihood. Very simple. It sounds very super easy, but if you keep doing this carefully, you will see one problem. Okay, I'll show you two figures to show what's the difference between the probability model of this lecture and the probability model in chapter 8. Okay, in chapter 8, it's a Gaussian mixture or cluster problem. We have unknown x here. We have observation y. Each sample is independent. Therefore, it's fairly easy for us to calculate a marginal a particular sample particular sample point. And again, it's very easy for us to calculate this Q function here, right? Because, okay, n here is the sample index, n here is the label index. And when we calculate the expectation, since they are independently distributed, we can put this E here inside the summation, which makes our life much easier. We just need to calculate the expectation of one particular data point, or one sample point. Therefore, every time we can get a closed form approximation onto this Q. And then we just find the maximization or maximizer is function Q. It's very easy, but for this model here, my question is the data points independent with each other? This is the vector X. So are they independent or not? What does this term look like, this higher term? This X is a vector X. It's not only one X, it's a vector X. This higher if the two pixels or the two nodes belong to the same sleeve, delta with one element belongs to the pi. So why we need a prior? We need to describe the relationship between pixels. This is the whole point of the prior. Without this prior, it becomes a very straightforward maximum likelihood estimator or maximum likelihood probability model. So in order to make our estimation more stable, or in order to dig out more information from the data, we make assumption saying that the neighborhood pixels, or if the pixels belong to the same fleet, they have certain correlation. We use this mathematical equation to describe the relationship between pixels, and this is the whole point of the prior. Therefore, in the probability model we propose in this chapter 12, the pixels are not independent with each other, which means we cannot use this strategy, which we have used in chapter 8 to find the closed form of this field theta. Okay, again, this field theta is too complicated. We cannot find a closed form. What kind of strategy we can have? You can think about your skill set. What kind of strategy you have learned?
EM, right?
Which I taught at the very beginning of this lecture.
Histogram.
Yeah, exactly. We draw samples. We have the form of the distribution. We don't know how to, or just to calculate the integral is too expensive. We don't want to calculate so many times the integral. So we draw samples from that posterior again and again for L times. Then we have a lot of samples. By using those samples, we can get estimation of the distribution. And we can substitute the complicated distribution or complicated function Q by the normalized histogram. Therefore, we get the EM algorithm shown here. This is so-called stochastic EM update. So this U here is defined as this term plus the constant. This definition of U. And we draw samples, and we get an X superscript L here. Then, by making use of this X, we can have a approximation of the two functions. After that, we can have the M-set update. Should be L by N. L by N. See the typo in the original note. And here again, we show the entire procedure of the EM-MTM algorithm, which actually we used to have a paper by a professor in EC department, Professor Palmer. He has a paper published in 2000 describing this EM-MTM algorithm for texture images. If you want to know more information about this segmentation strategy, I think it's a good idea to go through this paper. This paper provides more detailed proof about the strategies we talked about today and show a lot of interesting results. For example, here, yes, this is the original image. Here, we see a lot of complicated textures in the image, and by using the algorithm, we first of all generate feature vectors for each of the pixels. And we apply this EM-MTM method, we can get very promising results shown in this figure. As you can imagine, it's not an easy task to segment this image.
Okay, so the basic idea of this NPM algorithm is, first of all, we use EM to estimate the value of parameters. Then we use the NPM estimate to estimate
the value of each of the pixels.
There are two chunks. It
consists of the two algorithms described. And okay, here is a very quick summation of the stuff in this chapter. In this chapter, we try to solve an image segmentation problem. We use the Bayesian framework to segment the image. We have observation Y and the unknown X. In the real problem, typically this Y will be a high-dimensional vector. I'll give you some examples about how to generate this vector Y. For each of the pixels, typically we use the ball filter.
Applied onto the image. And ball filter
can detect edges or lines or any kind of like saliency point in the image. And for each of the data points XS, we apply a double filter, we can get a vector Y edge. And this is so-called feature vector. And by using this feature vector, we can segment the image by estimate how many classes or how many regions we want to segment from the image. And we can estimate what is the meaning of this feature Y and what is the variance of this feature Y. And by estimating those parameters, we can use a Gaussian model to approximate or to model the image. And after that, we can segment the image. And in this chapter, I think there are several things I think which is important. The very first thing is the difference between map and NPM. Again, I want to highlight that map and NPM, they come from the different cost functions. MAP estimation comes from a very conservative cost function, which has only two values. If that's immature and the ground truth is exactly the same, the cost function has value 1. If there is any single difference between those two vectors, the value of the cost function is 1. So by minimizing that cost function, we can get MAP estimation. And so NPM does not assume that we know the value of all the other pixels when we ask the NPM. The cost function NPM calculates the summation of error of the different two vectors. So it's more descriptive to the image. And you can imagine that NPM is more robust to noise or is less sensitive to noise. Here's a paper called the probabilistic solution of ill-posed problems in computational vision. You would like to take notes on this. And in this paper, the author shows some very interesting results by using MAP and NPM. So this one is a ground truth image. This is X, and we leave X randomly, and this is our observation Y. And as you can see here, we want to segment the image from this image Y. Even human cannot do that. And if we use map estimation to estimate this image, what do we get? We get a purely black image, which means map cannot solve this problem because the signal ratio is too low. But if we use NPM to build the result, it's amazing. If I handle this image to human beings cannot do that. So if we handle this image to an algorithm, this is also the algorithm, and this is the ground truth. It's a very promising result. And why NPM can get better solution or better performance than
MAP for this given particular problem.
okay, I said, okay, their cost function is different, but I'll give you some numerical reasons why they have different performance. Okay, for the map estimation, what kind of algorithm we solve map? We use ICM map algorithm. What does ICM mean? I'll show you the flowchart of ICM. Here is the flowchart of SEM. The basic idea of SEM is
The same as the previous
of ICD. So see the pixel values
of all
the other pixels. We have like initial guess. We fix the initial guess, and we just
update one pixel here.
which denoted by XS. Other than this particular pixel, all the other pixels got fixed. They have a fixed value. If the initial guess of all the other pixels is not correct or is incorrect, we will have a bad estimation with XS. This is why we have like a global conversion issue by using MAP method. I'll give you a very simple example.
We have only two nodes in the image. This image has only two
Pixel 1 and pixel 2. If we have a bad estimation at pixel 2, it's not easy to get a good estimation on this pixel 1. Because for map estimation, we fix the value of pixel 2, even though the estimation of pixel 2 is not correct.
This is a map ICM.
But of course, we have a lot of strategies to improve the performance. For example, like a kneading strategy, simulation and kneading.
I can talk a
little bit more about the kneading if we have time by the end of the lecture. But for the MPM, when we update pixel 1, what do we do? What kind of distribution we have here? Exactly. We maximize this marginal distribution. And how we get this marginal? Okay, maybe you got confused because we use like a histogram to approximate. But if we have only two pixels, we can
write down this way. x1 integral the p x1 x2 y x1 x2 y. Calculate the integral
over x2 to get the marginal, which means we do not assume that we already know the value of the pixel 2. We calculate the integral. We consider all the possibility values of x2, and we weight the probability of x2 by its probability. It's more like a weighted summation of x2 over all the possible values of x2.
Then we get the marginal of this
px1
given y. So it has better performance when the noise when the data is
it's very noisy, because we are thinking about all the situations. This is why
we can get a much better performance
by using NPM from this given problem. So, what is the disadvantage of NPM?
Tough to get the marginal.
Exactly. Okay, first of all, it's tough to get marginal. It's very computationally expensive. Even we use sampling method, it's still much more expensive compared with
MAP.
And okay, this question is kind of my favorite question, but I'm sure this question is not covered by this class.
So the MPM can be sure to converge to
The global minimum or global maximum. It's a little bit tricky question, to be honest. How to update NPM to maximize this
normalized histogram. This is how we update that. So is it
exactly the same with the marginal distribution?
Well, yeah, what? If L is really, really big, it should
Yes.
converge, right?
Almost surely converge to it. But in the real implementation, the L cannot be that large. And it's just
approximation of the original marginal?
right? Therefore, it's not even a maximizer of the original function. Okay, it's approximation. It's maximized approximation of the original function. Therefore,
The solution or the estimate tool of
NPM is not even a maximizer of the pulse function.
but it's so
So,
that on average it gives us
better performance. So this is the beauty of beautiful part of the NPM algorithm. And do you have any questions or
Also, the cost of processing goes way up if you have more than one class, right?
Exactly.
Advantage.
exactly?
But math is not too bad. How do you do it?
Yeah. Do you have more questions about this lecture or suggestions? Any kind of thoughts? This is a very long lecture. I cannot let you go before the class is over. So since the final examination is coming, maybe you want me to talk about the finals. And okay, I have good news and bad news. The good news is that actually the bad news first. The bad news is that I know nothing about the final. Okay. The good news is that since I know nothing about the final, I can give you some suggestions or advice about how to prepare for the final. If I know anything about it, I cannot say that, right? So, this is one of my favorite lectures during my PhD study at Purdue. It's very useful for my entire PhD research. And here are several tricks to prepare either the finals or prepare how to study this lecture. The most critical part is the lab. I think professors give us very flexible deadlines for due date about the lab. So students typically they don't can submit the lab until the very last minute. But I think the lab is very intuitive and very informative to study with. And if you check the instructions of the lab, they are not questions actually, they are instructions about how to do it step by step. So it gives you very clear instructions. Therefore, first of all, I strongly recommend you to implement or do the lab way before you start review or study the stuff or learn the stuff in the lecture. And if you have any, I'll write down my email address again. Here's my email address. If you have any questions about the lab, feel free to drop me an email. I'll try my best to get back to you as soon as possible. And after the lab, there are a lot of questions after each of the chapters. I'm not so sure you're not required to write all the questions. To answer all the questions after each chapter? No. Okay, I don't quite sure about the requirements of this course, but I really encourage you to go through all the problems of each of the chapters, and not only to learn things from this lecture, and personally, I think that is the very best way to prepare for the exam. Obviously, the questions exam will have similar flavor chapter question. Does Professor Coleman give you like samples down or?
No.
Maybe you can email him to ask him to post a sample exam or something like that and give you like a better idea of what kind of questions to create.
Based on my, it will has the same flavor as the question asked for each of the chapters, and I don't know whether we have enough time to go through all the questions, but at least we need to go through some. And there are a couple of things which I think are very important for this class, also for this topic. One thing is the probability model. We have two terms, likelihood term and prior term. Using the likelihood term, we feed our estimation to the observer or to the observation one, and for the using the prior, we make like additional assumptions onto that prior, and it's like a trade-off between two terms. And in order to estimate the parameters, we introduce an EM algorithm, which is in chapter 8. I think it's very important. And the probability model I just mentioned is in chapter 7. We use that model, pretty much exactly the same model to solve a computational imaging problem. And I believe Jeff Emaus used to visit Purdue 1 month ago, and he talked with Professor Coleman privately. One of the reasons is that we use this model covered in this class to solve a problem GE has, and we got a big success. Deep sampling gives you a more theoretical understanding about the stuff. Why we can use this kind of prior model to model the image that is covered in chapter 11. If you want to know more about how to approximate the posterior distribution, I'll introduce you a paper. I don't remember the exact name of the paper. It's called Expectation. This paper describes another algorithm to approximate very complicated distribution or a very complicated posterior distribution. Actually, I read the paper, so. What else? What other things you need to know? Do you have any other questions? Any questions? One is
I have a question, but it's about one of the labs. I don't know if you have the document in front of you. Probably not. Maybe that's for after class.
Yeah, we can talk about that after the class. I'll take lab. Any questions?
Is Dr. Bowman going to be here for the final? Is he going back over the weekend, or is he going to be still traveling over the weekend?
Good question. That is something I don't know. I believe he'll be back either today or tomorrow.
Oh, okay.
And whether he will be here for the final or not, that again, I'm not sure. If he is not here, I will be here.
Right.
And he went to the Global Seed, which is one of the most important. Okay, it's the first huge IEEE conference. IEEE hosts a huge conference covering almost all the topics, engineering, image processing, like financial engineering, everything. It's like another EI, but it's by IEEE. They invited the Professor to be there to talk, standing talk at that. Okay. I'm very glad that time's up, and very best luck to your final, and enjoy the weekend.
Okay.